I think we can handle the introduction from here. My name is Tiba Majid. I'm production engineering team lead in SLB with more than 8 years of experience working in oil and gas companies. And actually, it's company because I started off with SLB. And I started off as a case hall petrophysicist and then moved to flow assurance production engineering, and today as a team lead. With us, we have Duha Arif, who's our production facilities engineer, process engineer, also in the production engineering team. Duha, would you like to introduce yourself?
Yeah, hello everyone. So my name is Duha Arif. I'm the production facilities engineer at SLB, and I joined SLB since 2022 as a process engineer and also as a production facilities engineer. So yeah, thank you for attending this session, and nice to meet you all.
Thank you, Ms. Tiba and Ms. Duha. And the topic of this webinar is Pipesim nodal analysis and vertical flow performance tables generation for reservoir engineering simulators. And we introduced Ms. Duha and Ms. Tiba. My name is Suhail Daoud. I'm officer at SPE Erbil Section who graduated from University of Kurdistan. I will be moderator for this webinar. Speaker's bio. Basically, Ms. Tiba introduced herself, but let's do it again. She have a bachelor degree in petroleum engineering, University of Baghdad, and production engineering team lead and branch champion of SLB Iraq, with more than 7 years of experience. Started with the production engineering, logging, interpretations, tech log, and other stuffs to work over operations simulations for real-time decisions making and overall production data management, diagnosis, forecasting. And with the Ms. Duha Arif is she is basically have a bachelor degree in chemical and petroleum refining engineering from University of Basra, oil and gas, 2022. Works as a production facility engineer at SLB. Work on supporting all production and process engineering quests for all symmetry and Pipesim use in Iraq. Welcome to our speakers. The mic is yours. Now you can present the webinar. So let me stop my sharing screen. Ms. Tiba,
Yeah,
now
thank you. Thank you, Suhail. Thank you. Let me share my screen. Okay. Can you see my screen now?
Yes, we can.
Okay. So, first of all, as you know, I'm Duha Arif and production facilities engineer. And our session today, actually, it's about Pipesim nodal analysis. First of all, we will talk about what is Pipesim, what is the main functionalities of the software. And after that, I will explain what is nodal analysis, what is the benefit of the nodal analysis, and how we can run the nodal analysis using Pipesim. So, first of all, what is Pipesim? Basically, Pipesim is a steady-state multi-phase simulator and used to model the flow of the fluid through the wells and pipelines, and has a lot of the capabilities. Let me go through them quickly. So, the first one is Olga-S mechanistic flow model. So in Pipesim, when it comes to hydraulic modeling or pressure drop calculation, it's use Olga-S mechanistic flow model, which is the industry standard multi-phase flow model available in the industry today. And actually, Pipesim has other correlations in addition to Olga-S, such as the elements. We have, for example, Binks and Prill. We have Hagdorn and Brown, and etc. Also, Pipesim has advanced BVT and fluid modeling, and has has number of BVT packages integrated with the software, such as we have a Symmetry engine. Symmetry is basically a process software or process simulator that we used their engine to integrate it with Pipesim to model the CO2 solids. Also in Pipesim, we have Multiflash BVT package. Multiflash, we use it to model wax and asphaltene using Multiflash. Also, we have Eclipse 300. We have Greek 2008, which is used for gas modeling. Also, we have, of course, black oil BVT packages. Also, Pipesim has detailed heat transfer calculations for calculating heat transfer and fluid temperature. Also, it's used to calculate the temperatures along the pipelines and inside the wells. And one of the most unique features in Pipesim is integrated wells and network simulation, meaning you don't need to separate software to model the wells and other software to model the network. You have the ability to model all the wells and all the pipelines in the single file. And of course, Pipesim is powerful in both sides, network and pipeline. So when it's come to well, Pipesim has comprehensive well modeling where we can model the well from A to Z. We can model the fluid, the completion, the casing, tubing, all the downhole equipment inside the wells, such as packer, sliding sleeve, and etc. So also, Pipesim has integrated GIS pipeline profile, which is utilize GIS, which is a graphical information system, to automatically build the pipeline networks and automatically capture pipeline elevations. Pipesim also have network prediction optimization. So basically, optimization in Pipesim, we give the software our objectives, such as I want to maximize the oil production, and also give the software our constraints, such as I want to minimize the water production. So after that, I run the network optimization, and the software will give me the optimum value for the choke settings, for example, or it will give me artificial lift quantities in order to meet our objectives. Finally, we have extensibility and automation, a framework in which we are able to communicate with the model directly without opening the user interface. Actually, this is an advanced feature in Pipesim. We can use it by using Python language, and you need to have like basic knowledge about Python to use this feature in Pipesim. So after we know these features and the powerful of the software, now let's go to the production system. So as you can see in this diagram, shows the typical production system component, beginning with the reservoir, including the well with all the tubing, with all the equipment inside the well, such as safety valve, choke. Also, we have the pipeline and surface facilities. So if I look to the system at the component level, each element will introduce a pressure change or pressure loss as the fluid move through the system. So as you can see here, if the fluid move from the reservoir to the sand phase, which is the area before the completion, we will have the pressure losses in this area. Also, we will have pressure losses when the fluid enter the well. We will have pressure losses because of the because of the safety valves. We will have a pressure loss when the fluid move from the from the bottom of the well to the top of the well. We will have pressure loss if the fluid um, flow through the valve. We will have pressure loss when the fluid move from the wellhead through the pipeline and through the riser. Also, we will have pressure loss through separator and when the fluid flow from separator to compressor and through pump. And finally, we will have pressure losses when the fluid flow from compressor and pump to the final, let's say, sales pipeline for gas and for the well. So, how do we calculate? How do we take benefits of these pressure losses in our system? And how do we calculate the flow rates? How do we know how much flow rate this well will produce? So by knowing the reservoir pressure and separator pressure, we can use nodal analysis to know how much production or how much flow rate this well will produce. So what is nodal analysis? Basically, the idea of nodal analysis, it's to select node somewhere in the system. This node will be the point of interest in the system where we will separate our system to two parts, which the first one is upstream and the second one is it's downstream, or we can say it as I'll call it as outflow. So the purpose of doing that is to separate the influence of upstream on the well from the downstream influence. So what does that mean is basically when we have like issue in our production, or the well is produce less than what we expected to produce. So we when we use nodal analysis, we can identify where is the issue. Is it in the reservoir? Is it in the tubing? Is it in the well? So this is the basic idea of nodal analysis. So generally, we took the node at the bottom hole, but sometimes nodes are selected at the wellhead, maybe the ESP intake. It really can be placed anywhere in the system, but as I mentioned, it's most too commonly it's done at the bottom hole. So once we select our nodal analysis points, as I mentioned, which separate the system into two components, the inflow component and outflow component. The inflow represents the pressure drop associated with the system upstream of the nodal point. In this case, where I choose the nodal point at the bottom hole of the well, the inflow it's represent the difference in pressure or the pressure loss between the reservoir and bottom hole of the well or the nodal point. Likewise, when we like this is the bottom hole or this is the nodal point I choose at the bottom hole of the well. So likewise, when we separate our system into two components, the outflow, which is from the bottom hole of the well to the wellhead, or in this case to the separator, this is called outflow. And it represents the pressure difference between the nodal point and the system outlets. As I mentioned, it could be the separator, it could be the wellhead. So as you can see here in this plot, which is represent the typical nodal analysis plot, it's plotting the pressure at the nodal point versus the flow rates. And we must define two boundary pressures in this case. So as I mentioned, we need two boundary conditions to solve our nodal analysis. In this case, I know the reservoir pressure and I know the separator pressure, which is represent the outlet pressure of this system. So that's mean the pressure of a fluid anywhere in our system will be between these points. Okay, so if I plot the inflow on this graph. So inflow, as I mentioned, it's the pressure difference between the reservoir and bottom hole, at bottom hole points, which is I chose as a nodal analysis point. So if I plot the inflow on this graph, we can see the curve. It looks like it's look like curve, and it's basically tell us if there is no if the well is shut in for a long time, obviously the flow rate will be zero. And if the flow rate will be zero, the pressure of the reservoir will be the same pressure of the bottom hole, of the well. So if I plot the outflow of the system, which is represent the pressure difference between bottom hole and the separator, as I mentioned, um, the as you can see here in this curve, blue curve, the outflow will like when the flow rate will increase, the bottom hole pressure will increase. Also, as you can see here in this curve, that means that the pressure required to move the fluid from the well to the surface increase when we increase the flow rate. So the intersection, as you can see there, the intersection of these two curves shows the operating point. Operating point, it's the theoretical flow rate that the system is capable of producing. So then we can use this as a basis to like investigate ways to increase the production. For example, if we fracture the well to reduce the skin factor. The skin factor, it's basically the damage in the formation, which will like increase our losses in pressure. So if I reduce this skin factor, the inflow, as you can see here, the inflow will be shifted to the right and result to increase the flow rate, as you can see here. And it's the same thing if I install, for example, an ESP. If I install an ESP in the tubing, we will shift the inflow, this curve in blue, we will shift it also to the right, and we will achieve the similar effect.
Ms.
So,
Duha,
yeah.
sorry for interrupting you, but one of our guests are saying, could you please repeat from where you separate the production into two parts, because there was an electricity cut from my side. So if you could please repeat it a little bit fast about that. And if
Yeah, sure.
anyone have any question, please raise their hand and or send it just in the group message. We will tell.
Okay. So, okay. The idea of nodal analysis, as I mentioned, is to split our system into two parts, the inflow and outflow. So let me just, as you can see here, the inflow curve in red, it's represent the pressure difference between the reservoir and bottom hole of the well. Why it's as I mentioned, I split the system, our system or our well, into two parts, but I choose let's say, the node of the nodal analysis at the bottom hole. Okay, so the inflow represents the pressure difference from the reservoir to the bottom hole. The outflow represents the pressure losses or pressure difference from bottom hole to the wellhead or to the surface. Or to the separator. It's the same thing. The idea of doing that, it's if I have like issue in our well, or the production is less than what we want this well to produce, we can say, or we can identify where is the issue. Is it in the reservoir? Is it in the inflow? Is it in the outflow? In the tubing? Maybe we can add ESB or change the diameter of the tubing. So this is the idea of nodal analysis. The intersection points of these two curves, it's represent the operating point Operating points means that this is the flow rate that I will have from this well at these conditions. Okay, so if I want to increase the production from this well, what did I do? I can do, for example, reduce skin factor. As I mentioned, skin factor is damage in this area. It's in the formation will cause to increase the pressure losses. So if I reduce the skin factor, that means I will decrease the pressure losses, and that will shift the inflow curve to the right, as you can see here, and that will cause to increase the flow rate, our flow rate from this well. Okay. The If I want to like add ESB, for example, in the tubing, the ESB will increase will shift the outflow, actually the outflow, this blue curve, to the right, and we have the same effects. It will increase the flow rate. So this is basically the idea of the nodal analysis. It's give me the, let's say, the flow rate from the well, and how can I improve it or increase it. Okay, so as I mentioned before, the inflow, which is the inflow performance relationship, it's in Pipesim. It's there is a lot of equations to calculate it. We have, for example, and of course we will see these equations in the Pipesim in the demo later. So the IPR can express using different equations depending on the various conditions, such as pressure, fluid properties, fluid regime, and etc. So we have a well productivity index equation, which is basically we use it for undersaturated oil, where the bottom hole pressure greater than bubble point pressure. Also, we have vocal equation, where we use it when the bottom hole pressure is lower than the bubble point pressure. Also, we have Witkowicz and packet pressure equations, where actually these equations we use it for turbulence flow, and this n represent the degree of the turbulence, and we use actually Witkowicz for the oil reservoir and packet pressure for the gas reservoir. Also, we have Jones method. It's modified BI and Darcy equation. It's also accounting the turbulent flow. We have Residue steady state, or Darcy equation, which is assume that the steady state flow conditions. And we have actually a lot of equations inside the Pipesim, and we will see it later when we go to the demo. So this is for the inflow. For the outflow, as I mentioned, it's before, outflow represent the pressure drop through the tubing, and in Pipesim calculated as a summation of a gravitational loss and the frictional losses and acceleration losses. So as you can see there in this equation, gravitational losses, it's depending on the fluid densities, distribution along the well, and this is sine theta, which is represent the elevation of the tubing. Also, for the frictional losses, it's depending on the, it's also depending on the density of the fluid, on the velocity, as you can see here in this equation of the fluid. It's also dependent on the flow. Is it turbulent or laminar? Because as you can see here in this equation, we have friction factor, which is depending on the on Reynolds number. So we need to know, is the flow is turbulent or laminar? Okay. For acceleration, we have acceleration loss is zero for the constant area, and if we have it can be more than zero if there is any change in the in the velocity of the fluid by pressure or temperature changes. Um, so it can be more than zero. And in Pipesim, uh, so it's actually it's for the acceleration losses, it's the smallest contribution to the entire by pressure drop, but it is still calculated by Pipesim. So Pipesim calculate all these types of pressure losses, which is we use it to calculate or to to calculate the outflow of the nodal analysis curves. So for now, I will jump to the Pipesim, to the software to build well. Let me share my screen. Now I will okay, give me 1 second. Okay. So
Majduha, there is no sound if you're talking.
oh, I'm so sorry. Okay. Can you hear me now?
Yeah, sure. Now we can hear you. It's okay.
Okay, okay. So let me go again. Okay, so this is when I first launch the software. This is the interface. Here we can create network workspace. Here we can create a well workspace. Here we have the all information about the license. Here we have the cases that I already worked on. So in this case, or in this demo, I will build well model. I will run the model and evaluate the model. So because I will build wells, I will choose a new well um, workspace. Okay, so this is the interface of the software. Here we have the interactive schematic of the well, where we can drag and drop the equipments from insert tab. We have casing, we have tubing, choke, backer, and etc. Or I can build the model by following these tabs from the left to the right. Okay. So for this example, I will add casing. first by drag it and attach to the wellhead and drop it. Okay, the casing will have the default depth as 10,000. Okay, next let's add tubing. As I said before, we can drag and drop it, or we can from this tab tubulars, I can add tubing. So now I will add the tubing from this row. So just click on the plus sign, the casing will be added. Okay, so for tubing, sorry, for the casing, as I said before, the depth will be by default is 10,000. I can change it, of course. For inside diameter thickness, I can enter the values manually, or I can choose it from catalog. From these three dots, I can open uh, casing catalog and enter one value. For example, for outside diameter, it's 7. Okay, enter and choose the first one and click OK. So now we have the inside diameter, well thickness, and reference. For the tubing, I will change the depth of the tubing to 9,000. Okay. As I said before, I can enter this value manually. So for the tubing, I will enter the inside diameter of 2.195. For well thickness, it's 0.34, and depth it's 9,000. Okay. Now, uh, let's go to the deviation survey. Deviation survey is to define if the well is vertical or horizontal. If the well is vertical, I just keep it as the default vertical. If the well is horizontal, I can, from the drop-down menu, I can choose 2D or 3D. It's both represent the horizontal well, but if I choose 2D, for example, I need to enter measurement depth and a true vertical depth. If I choose 3D, I need more data. So it's dependent on your data. For this case, I will choose the vertical because the well is vertical. Okay. On heat transfer tab, I will specify the soil temperature as at wellhead, which is the wellhead temperature, for 65 degrees Fahrenheit. Okay. Now, for now, I will keep the downhole equipment and artificial lift as default for now, and we will come back to this later. For completions, let's add the completion. Completion basically it's the point of contact between the reservoir and the well. So as I mentioned, we can add the completion by drag and drop it, or we can add it by click on the plus sign. So this is our completion. Uh, Here we can choose if um, if the completion vertical or horizontal. Here we can enter the depth of the completion. For this case, it's 9,500. Okay. Um, this is what I mentioned before in the slides as IPR model, which is the equations that will calculate the inflow curve. Okay, so now I will keep it as default. You can see here we have wall PI, we have vocal, we have vid COVID, Jones, packet pressure, and etc. Okay, we choose it as we mentioned before, dependent on our fluid. Okay, so for this example, I will choose or keep it as default. Well, productivity index. For reservoir pressure, we have it's 5,000, and for the temperature, reservoir temperature, it's 200, and for the productivity index, it's 1. Okay, so now the plot of IPR does not display it, right? Because I've not defined the fluid model. Okay, so now let's create the fluid. I can create the fluid from fluid model by click in new fluid and choose light oil plus gas template and click OK. Okay, now let's specify the information related to our fluid, which is gas oil ratio. It's in this example 500 under cubic feet per stack tank barrel. And for the water cut, it's 25. Okay, and I will keep the specific gravity for gas for water as default. Now, by close this window and come back to reservoir, you can see the inflow curve displayed here. Okay, now uh, let's check. So if I uncheck this box, as you can see, this box is use vocal below bubble point. If I uncheck it, you can see here the inflow curve is straight line. If I check it, you can see it's updated and now we have curve. That's because after the bubble point, we will have gas formed, and this behavior, it's because the gas, and we will see later on the results how that affects on our results. Okay, after that, uh, let's check the schematic of the well. As you can see here, we have like the flow path of the fluid represented by green lines. And as you can see, the fluid is a flow through the tubing and through the annulus, right? So to isolate the fluid flow like to make the fluid flow only through the tubing, we will add backer. I can add it from downhole equipment or by drag and drop. Let's add it from here, from downhole equipment. By click this plus sign and enter the depth of the backer, which will be 8,710 feet. So as you can see, this is the backer. Isolate the fluid from a flow through the annulus, and now the fluid, it's only a flow uh, from the tubing. Finally, let's add surface equipment. How can we add surface equipment from this tab? Surface equipment. I will add choke and sink. It's basically by drag the choke into the schematic of the well here and add the sink. Sink, it's we add it to represent the delivery points of the well, of this well. Okay, so to connect the choke and the sink, I will use a flow line from insert tab. Okay, it's the same idea. Drag and drop it and connect these two equipments. To connect the well and the choke, I will use connector. Why I use connector in this case? Connector is basically used when there is no physical distance between two equipments. For example, between the well and the choke, there's no like distance between them, and there is no pressure loss between them. So we connect them using connector. Okay, by click on the choke, we need to enter the pin size of the choke. So it's in this example, it's 128 to 64 fourths of the inch. Okay. And also I will click on the flow line to specify the information related to flow line. We need to enter the inside diameter. For this case, the inside diameter will be 3 inch. and the horizontal distance will be 2,500 feet. Okay, now we will, the well model is complete, and we can now run the, like we have several tasks in Pipesim, such as PT profile, nodal analysis, system analysis. Let's see them there. This is the task where we can run actually BT profile or pressure temperature profile. We use it if we have like, if we have two values, inlet pressure, outlet pressure, and we want the software to calculate the liquid flow rate. Or maybe I want to calculate the outlet pressure and give the software the liquid flow rate. This is the idea of BT profile. For the nodal analysis, before we run the nodal analysis, it's the best practice is to check the validation from this tab. Validation, it's when it's green, that means there is no missing data. That means we can now run the simulation and get the results. So now I will run a nodal analysis task from Home tab. I will choose nodal analysis and choose the location of the nodal point. As I mentioned, we can choose it in the bottom hole here, there, and we can choose it in the wellhead. Okay, so for this example, I will choose it in the bottom hole of the well and click OK. So if you remember previously in the slides, we said we need two boundary conditions for nodal analysis: the reservoir pressure and the outlet pressure, which is the separator pressure or wellhead pressure. Okay. In this case, I already entered the reservoir pressures in completion, which was 5,000. And for the outlet pressure, let's say it's 250. Okay, now I can run the simulation. It took, it doesn't take a long time. So this is the results. As you can see, after the simulation has been run successfully, we can see the nodal analysis plot. This is the curve to represent the inflow. This curve represents the outflow. This is the operating point, which will give me, it's around 2000, and yeah, it's around 2000 for liquid, and at the pressure of 2000, or it's around 3000 actually. Okay. What I can do is to click this box to show the purple point in the results. Actually, I can also show the operating envelope. Operating envelope, it's to specify, it's bounded by the maximum erosional velocity. This line, it's represent the maximum erosional velocity. So if this operating point it's outside this box or outside this line, that means I will face erosional risk in our well. Okay. Also, we have maximum drawdown limits. We have in this line reservoir pressure. We have in this line the inversion point for stable
Mustafa,
liquid production. Yeah.
I think the screen is frozen. Some of the people are saying, like,
Um, okay, let me stop sharing. Okay, now. What I was saying is, if the operating point outside this box, that means I have issue in our well, and I need like to identify the issue and try to like um, override it. Okay. So also in the nodal analysis task, we can see the results from the profile results uh, as a table. it's here we have the total distance, elevation, pressure, temperature. Here we have the liquid holdup. Liquid holdup. So for this part of the system where we have only liquid,
Miss,
okay,
I think
where
you cannot see
yeah,
it because it's on the application, Pipesim application.
no, it's not. Let
We
me
are
stop
just
sharing.
Pipesim.
Um,
I think you should share the other screen because it might be two
yeah,
screens.
yeah. Not two screens, but can you see the screen now?
Yeah, we can see it right here.
Oh, okay, okay, yeah, I guess. Okay. Now, you can see now the nodal analysis window, right?
Yes.
Good. Um, okay, we were here in profile results. Profile results, it's basically to show the pressure as a function of the elevation. So we can see here the pressure losses. We had there, we have the pressure is constant, or it's the pressure losses through the reservoir. And in this point, this is the bottom hole pressure, and this is the pressure losses through the tubing. We can actually select, for example, temperature. We can select, for example, liquid holdup. Okay, to see the liquid holdup fraction as a function to the elevation from the reservoir all the way to the surface or to the separator. Okay, um, we can see the results as a table, as you can see here. This is the holdup. Holdup in this part of the system where we only have liquid, where the liquid holdup is 1%, 100%. So in this case, Pipesim used to calculate the pressure losses productivity index model. And after we pass the bubble point where we there where the liquid holdup decreases, where we have where the gas is formed, as you can see here, that now in this part of the system, the software use vocal equation to calculate the pressure losses. And this is the benefit of checking this box, is to use will PI for the first part of the system and vocal for the second part where we have gas. What we have else? For example, if the pressure, as I mentioned before, like it's if the pressure at the reservoir decreases, that will affect the production of the well. Let's say, for example, if the pressure of the reservoir decreases to from 5,000 to 4,000, okay, and I can choose or check this box, override phase ratio. Override phase ratio, it's enable me to change the fluid properties. For example, I can change the GOR, I can change the water ratio or water cut. For example, I will like put 80% water cut, okay, and run the simulation. So as you can see here, if the reservoir pressure decreases, there is no intersection between the inflow and outflow. That means this well will be unable to produce. So if I look at the nodal analysis, I can say that, okay, to solve this issue, I can, for example, install ESP. I can, for example, change the choke at the wellhead, and etc. So yeah, I think this is all for the nodal analysis. If you have any questions, if you have anything to add, please feel free to ask. And thank you for your attention. Thank you for your attending this session.
Thank you very much, Ms. Doha. If it is finished, I think we should answer the questions if anyone have any questions. Abdul, could you please tell us what's your question? If anyone have any question, write it down in call message so we can answer the questions. I'll try to open your mic. Wait 1 minute.
طبعا هذا البرنامج هو برنامج البايبسم اللي هو الستدي ستيت سيميليتر مال شركة SLB. أنا شفت واحدة من الأسئلة كانت هو ما هو اسم البرنامج المستخدم.
السلام عليكم.
عليكم السلام مستر عبدو.
وعليكم السلام.
أول شيء شكرا للبشمهندسة على الشرح الوافي، جزاك الله خير. معلش عندي بعض الأسئلة، سؤالين أو ثلاث. أول شيء بالنسبة في التاب في الكومبليشن at reservoir, you choose the when you choose tick of Vogel bubble point, there is another option for water correction. Excuse me, Ms. Duha, if you can share the screen, or
Yeah.
can't. Yes, of course. Vogel water cut correction. When we choose this option, I mean, which ratio or which percentage for the water cut we can use this option?
إذا ممكن ضحى أخذ الجواب أنا على هذا السؤال. طبعا هو أستاذ احنا نستخدم هذا الأوبشن غالبا لما يكون عندنا واتر كات يعني فوق 30%، إذا نريد يعني نحط لنا فد ريشيو. هي الفكرة من عندها أنه الويل برودكتيفيتي اندكس مبني على أساس السنجل فيز فلو، اللي هي احنا راح نتعامل ويا الأويل ريت والبريشر ديفرنشال والميو أويل والبي أو مات الأويل. تمام. فاحنا هنا قاعد نحكي عن معادله takes into consideration the presence مالت الاويل، فلما يصير اكو عندنا احنا production مالت مي وياها، هذا راح يضيف inaccuracy لما احنا نستخدم المعادله. فممكن يعني انا انطيك انه 30% of water ممكن ان تسبب احنا عندنا يعني underestimation اذا صارت فوق ال 30، فبهيج حاله ممكن انه انت تستخدم الواتر كات كوركشن. طبعا الشغله الحلوه انه انت ممكن انه you check the box خل أكمل الجواب بالإنجليزي. So
Okay,
you
no.
can check the box. Yes, you can check the box anytime and you will be able to see the difference. Usually below 30%, the difference it's there, but it's, let's say, it's minimal. Above 30%, you will see differences. There are cases like where you have 70 or 50% water cut. You know, it can actually cause an underestimation of maybe 2,000 barrels, etc. It depends as well on the deliverability of the well
Good.
we're trying to analyze. So in any case, you can always check or uncheck the Vogel water correction, and you can see how much difference it makes. Okay.
Okay, thank you for this answer. Also, it's depend on the IBR model, or it's for all models. You mean your answer? You answer. I mean, apply for all models like will be like Vogel, like Vorkovich.
So this, I think it's present in the well PI and in the Vogel. Duha, maybe you can try and check. Let's say Vitkovich. Yeah, I think So yeah, it's not there. So it's only in the well PI.
Yeah. Okay. Shukran for your answer. Also, just quick information about the sink. What you mean here by sink? This is you mean by any storage or any end of the pipeline shipping, or when you choose sink for your
Yes. So Duha, would you like to take this question?
Yeah. Sink, it's represent the delivery point. So to how do we know how much flow rate we produce from this well? We add the sink, and from the sink, it's like it's not stored. It's just in the software to know how much flow rate we will produce from the well, and to know the wellhead pressure. In case if we model the network, we can add the sink and, for example, model the entire network, and we run the network simulation. So by adding the pressure, wellhead pressure, we can calculate, or we can estimate the flow rate for the network. Yeah. So this is the sink. It's only in the software.
Okay, that means it's the same. Let's say separators or stores. That means something end of our flow line.
Yeah, it's the end point of our flow line or our system. Or our network. Yeah.
Thank you. Sorry, there is, for me, that's the question. If there is anything else,
it's fine. Take your time.
you just estimated the wellhead pressure, which is like you said 2 barriers in the software. I mean, reservoir pressure, and you estimated the wellhead pressure, which is 250, I think.
We don't estimate it.
Let's say you put it, you choose it. Yeah. Okay. Just there is like a curve. I don't know now, or the next page, or there is the floor. Let's say in flow curve.
I think you're referring to the nodal analysis, the inflow and outflow.
Yeah. So just I need to know if you remember, you changed the pressure, and you choose temperature. So I don't know which page, because you changed the curve. It belongs to required. You mean if you need the temperature, you will show the temperature. If you need pressure, you will show the pressure.
Yeah, I got it. From profile results.
Your profile, yeah.
Yes, profile. Yeah. There we can get this chart, which is represent the pressure as a function to the elevation. Of course, we can't change the pressure. For this example, in this case, this is the pressure profile for the well. This is the pressure losses through the reservoir.
I think you want the screen is frozen for me.
I think it's because of the sharing setup. So you're just sharing the node, the
because
pipes.
My question, I have to see the the chart to
Yeah,
show
yeah.
my question.
Okay.
Sorry if I takes time for.
No, it's
No,
fine.
it's okay. It's okay. So in the meantime, while Duha tries to present, okay, yeah,
O-
there it is.
Okay. So this is in the profile results. This is the chart which, as I mentioned, represent pressure versus or as a function to elevation. This is a pressure drop in the reservoir, and this is pressure drop in the tubing. I can change the pressure or the x-axis. I can change it, for example, to temperature to see the temperature profile with the elevation. I can change it, for example, let's say liquid hold up, we can change it to original velocity ratio. It's there's a lot of variables there. For example, this is the liquid hold up. Also, we can change the y-axis. It's not it's to change it to, for example, erosional rate, erosional risk, and etc. There is a lot of variables there. And yeah, this is the idea of this chart.
Just can we back to the pressure option?
Pressure, yeah, of course.
So in the left side, the elevation, the zero scale, that mean the wellhead, right?
Yeah.
Yeah. So I think it's start from 200, 250 or from zero now pressure.
Now it's start. This is the this is the reservoir pressure, and yeah, it's at the wellhead.
It's like a zero
actually
now, the pressure.
let me zoom. Because we changed the nodal analysis there. If you can see, this is the another case. Let me check it. 1 second.
Yeah, it's unconverged, which means that we don't have
Unconverged.
flow.
Yeah.
That's why. I think if you change the reservoir pressure, because in this example you reduced the reservoir pressure and tested, right?
Okay. Yeah. Right.
Yeah. Or maybe the water ratio. Yeah. Let's try and show the grid.
Mm.
It should be around 250. Yes, it's 250.
It's
yeah. Because this is what we specified in the nodal analysis setup in the first tab. If you can go to the first tab. Yes, so the outlet pressure was already selected. It's 250 psis. That's why, the system here is, generating the inflow and outflow curves based on the outlet and inlet pressure and the IPR model that we selected, in addition to the configuration of the completion and the PVT. So based on that, if you can go to the system results, yes, so it calculated the pressure for this case when the wellhead pressure is this much, when the reservoir pressure is this much, when the water cut is this much, and it's around 2080 STB per day.
I don't know if you understand my question, but my question is just it's should the curve start from 250? I think the curve. That's my question. It's not like a zero, but I don't know the system. Maybe this is my understanding. if I am wrong or right.
Hello?
Hello?
I've been talking, yeah, but I was muted, so sorry.
Ah,
I've been
sorry,
trying to
even.
explain, yeah, obviously you haven't heard anything. But the funny thing is that Duha was actually moving to the tabs that I mentioned. So anyways, so I was talking about the nodal analysis, the fact that if you go to profile results, Duha, can you please go to profile
Yeah.
results? Yes, you see the flow rate here is calculated by Pipesim based on the inputs. Our inputs were the reservoir pressure, the output pressure, which is the pressure at the, at the wellhead. So we actually told the software that the wellhead pressure is 250 psi's. So based on the inlet and outlet pressure, based on the well configuration, the PVT model that we have, what will be the flow rate and what will be the PWF that corresponds to this flow rate for the system? Is it going to flow or not? So this is what we were trying to understand, from the nodal analysis. So if you see, the software calculated that the flow is going to be 2080 barrels per day, while the pressure is going to be around 2900 something at the node. If the wellhead pressure is 250, if the reservoir pressure is around 4000 or 5000, if the water cut is 25%, and so on.
Mm.
Is it clear? So the elevation is 0, yeah, but the pressure is 250, which is the wellhead pressure, where the elevation is 0 because we are at the top. Yeah?
Yeah, sure. I got it, this idea. Yeah.
Mhm.
Thank you. I don't know who speak, Miss Duha or another.
طيب.
Yeah, we were
Thank you.
working, we were answering the question together.
Okay, thank you. And I'm so sorry if it takes time for my questions.
No problem. We actually, we still have 15 minutes for questions.
Yeah,
So if you have more
because
questions, go ahead.
yeah, thank you. Because just the Pipesim, I don't use it too much, but I just use software for ESP design, like belongs to SLB, which is
Well, there are a lot of applications actually, one of
yeah.
which are the vertical flow profiles, which I think we have a question here. So, yeah, it's regarding the VLP table. In the case of reservoir simulation, do you need to generate so many tables for each well in the model? Otherwise, is it okay? Is it okay enough to generate one general VLP table to cover so many wells in the model? So, the answer is, one of the applications that we use Pipesim for is to create the VLP tables. The idea is that the reservoir simulators can simulate the fluid flow inside the reservoir to the well, but to be able to accurately simulate the flow inside the well and understand if the well will be able to lift this fluid from the bottom to the wellhead, we need the steady state simulators like Pipesim in order to create these VLPs, which are basically the outflow curves of the its system. So we take into consideration the effect of the well bore components on the flow. For example, the tubing ID, if we have water cut, etc. With the well configuration, with the fluids being produced, will the fluid flow from the reservoir, from the bottom of the well to the wellhead or not? So this is actually what we need the steady state simulators for. As to the VLP table itself, we can actually generate it in Pipesim, but it's generated per well. So we can select the scenarios or the sensitivities of different components that impact the outflow curve of the well. And we can actually select the simulator, the reservoir simulator that we want to export these VLP tables for. For example, is it Eclipse? Is it, whatever reservoir simulator? And based on that, we will have the output files generated. Okay.
Well, thank you for your informative answer. Yeah, basically, also want to know about mostly in the past. What I understand is to generate the BFP gas is in order to calculate what we call tubing head pressure. So basically, let's say that in Euclid, we ran the simulation without putting a BFP gas. So however, we get the result, right? But when we put the BFP gas, the only difference what I found is that it calculated tubing head pressure only, but the result is almost the same. So I just wondering what is a bit different or adding the BFP gas.
Can you please repeat? Why is it different?
What's the big difference between by adding the BFP gas or not? Yeah. So actually, what I understand is that it calculates only the tubing head pressure.
Oh, okay. So you want the difference in
Yeah. The difference.
calculating the tubing head pressure?
I mean,
I
normally
think
in
your voice is interrupting. Maybe it will be easier if you can type, because I don't know. I could not. Yeah, I will appreciate if you can do that. Yeah,
I
you
can
can
type
just
it.
yeah, because I think the line is okay. In the meantime, let us have a look at another question. Okay, there is a question. How can we detect which parameter affect on the production rate based on the nodal analysis? This is actually done by actually selecting the sensitivities for inflow and outflow. Mr. or Miss Ariane, yeah, if you're still there. So this is where we can actually, understand the effect of each parameter on the nodal analysis, or basically the well performance and production. So we have the inflow sensitivity and we have the outflow sensitivity, and there are components that we can base our sensitivities on. And then once we run the nodal analysis, we should see the different scenarios or outputs based on the sensitivities. Maybe Duha can try and have an example here. Yeah. Run the scenario.
For inflow sensitivity, let's try water cuts, for example. Let's try, for example, 0, 5%, 10, and let's say 40. Okay. Okay. Now we can run. Yeah. So this is the result. You can see there, if we have water cut 0, the liquid production will be 2,300 and something. If the water cut is 5, the water or the flow rate will be 2,200 and something. And if the water cut is 10%, the liquid flow rate will be 2,200 and something. It's less than this one. If we have water cut 40, for example, it will be 1,900. So yeah, from there we can see the effect of, for example, the water cut on the production rates by using nodal analysis.
Okay, so yeah, so Mr. Mate Zin, okay, so I actually just typed the reply and for your question. So you mentioned that you tried two cases for simple model with and without the VLP curve. The only difference that you found is the one with the curve. Of course, calculate tubing. Okay, again, I was talking while mute. I think it's an issue that I will need to focus on later. Okay, yeah, Mr. Zen, did
Yeah.
the comment section, yeah, did I answer your question?
Yeah,
I
exactly.
replied
Yeah.
in the
Yeah.
comment. Yeah, okay.
Yeah.
Okay, good.
Yeah. Very informative. Yeah.
Okay, great.
Meanwhile, I also had one question. Can I ask you?
Yes, sure. Tell me.
When you did the demonstration here, I didn't see you choose the correlation like a Bragg and Bay, Hagedorn, such a. You didn't choose the correlation, right?
Yes, we did not go into the settings, the simulation settings. But of course, in any simulation, we need to go and select the simulation that works best for our, for our model. So of course, we have the correlations and we have the mechanistic models. We have ones for vertical and we have ones for horizontal flow. And each one is, let's say, for the correlations, basically they're designed for certain conditions because they're mathematical, statistical, models, let's say. They're built based on a set of, like wells of certain characteristics, parameters, etc. And then they try to find the relationship between these, let's say, wells that are, that they build the correlation based on. So you have to always check if your well agrees with the correlation and which correlation was built based on data that matches the well that you're trying to model. On the other hand, we have mechanistic models like Olga. Olga is a mechanistic model that was Olga steady state. It's a mechanistic model that was developed by SLB, and a lot of investments were done in order to build this model. It's meant to be applicable for three-phase, any well, let's say trajectory deviation, to simulate horizontal or vertical flows, two-phase, three-phase, and basically any type of fluid. So, you can also have the model calibration. There's an option where you can actually insert some well test data, actual measurements, and then compare the outputs of the simulation using different correlations or different mechanistic models, so you can determine which one gave the best or the closest results after doing the calibration to the actual measurement. So it's another workflow, or let's say it's another process. If we want to do it, we're not going to have enough time today because we're going to have to go into the catalog. We have to put the well test data, and then we have to go to the model calibration, select the models, and then run them, and then have a look at the root mean square of each model after the calibration, and then decide based on that which one gave us the closest match with the tubing head pressure, and then based on that we can decide. Of course, there are other considerations, but the one that we usually consider the most, let's say, is the tubing head pressure match, because it determines if the pressure losses were accurately calculated throughout your whole system. And then based on that, you can actually populate the one that gave you the lowest RMS for for the matching, and use it in your simulation. But we didn't go through these steps, and we did not go through these through this workflow for the sake of time. Maybe we can in future have another session that discusses this aspect. Okay.
Yeah. Okay. Yeah. Thank you so much. Yeah. Thank you. Very informative. Yeah.
Most welcome.
Thank you very much, Ms. Tiba and Ms. Duha, for this webinar. It was very helpful for everyone, I think, in this meeting. If there is
Thank you, everyone. Yeah, sure. If there are any questions, I think we still have 2 minutes left to catch up. And thank you, everyone, for your attendance. Thank you so much for the questions. Thank you for the interaction. And we hope you found this webinar very helpful. And hopefully we will have the chance to present again in future. Yeah, thank you, of course, to SPE Erbil Section for enabling this webinar and the series in general, actually. You've been very collaborative and very helpful in helping us spread the knowledge.
Thank you, Ms. You're always here to help students and professionals who want to learn more about any type of subject about oil and gas industry. And thank you for both of you. You did very well. Thank you. We appreciate
so
it.
a special
Thank you.
thanks actually to Duha, because she's on vacation and she did take time to prepare the slides, the examples, and to present, which was, it reflects the level of her commitment to sharing knowledge. So thank you, Ms. Duha.
Thank you, Tiba. Thank you.
Thank you, Ms. Duha.
Thank you all for joining this session, and have a good day.
You too, everyone. Thank you.
Thank you.
Bye-bye.